Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here with another video on your ZyBooks. This is section 8.6, titled Strong Induction and Well Ordering, or the Well Ordering Principle. So we saw in sections 8.4 and 8.5 an introduction to the principle of mathematical induction. Right, where you had to prove a statement about integers greater than or equal to 1 or 3 or whatever. You showed that the statement was true for a base case, right? And then you had your inductive step, where you assumed that the statement was true for n equals k, and then showed that it had to be true then for n equals k plus 1, right? The next integer up. Well, here we're going to see the principle of strong induction. Sometimes more than a single base case is necessary to be able to prove a statement about integers and a statement involving integers with induction, and we'll see that here. So I'll read through their example they've got here as to why this principle of strong induction is necessary instead of just plain old induction, and why in some cases you might need to prove more than one base case to get your proof by induction going. So the Fibonacci sequence, remember, is defined by initial values. F0 is 0, f sub 1 is 1, and the recurrence relation, right, for n values of n greater than or equal to 2, f sub n equals f sub n minus 1 plus f sub n minus 2, right? Every term of the sequence is the sum of the previous two terms. Now, suppose we wanted to prove an upper bound on the Fibonacci numbers, such as the nth Fibonacci number is always going to be less than or equal to 2 to the nth power. And this, say we want to prove that for all n greater than or equal to 0. So let me show you what happens, what goes wrong in the standard form of induction. And I'm going to show you on some paper what would go wrong if we tried to prove this statement with the induction that we've seen, right, the standard form of induction. So here's the theorem. All right, given the Fibonacci sequence, they're saying the nth Fibonacci number is less than or equal to 2 to the nth power for all n greater than or equal to 0. So remember the standard induction. Right, so if I tried to do a proof using the mathematical principle of induction that we've seen, I would try to do it in the following way. Remember, there was a base case. In this case, we're trying to prove this statement for all integers, greater than or equal to 0. So the base case would be, when n equals 0. Well, put this in, is f sub 0 less than or equal to 2 to the 0? Well, this is 0 is less than or equal to 1, and this is true. All right. So it's true for this base case of 0. And then with standard induction, right, what we've seen in the previous couple sections, we had our inductive step, where then you were trying to show that for all integers k greater than or equal to the base case, greater than or equal to the base case value of 0, the following: if the statement is true when n equals k, right? So if f sub k is less than or equal to 2 to the k, then we must show that the statement will then be true for when n equals k plus 1. So f sub k plus 1 is less than, show that that's less than or equal to 2 to the k plus 1. Right. So we had our induction hypothesis, right? We would assume this, right? We'd assume that this was true for values of k, greater than or equal to 0. And then we try to show this, right? And this was called our induction hypothesis. So I'd, over here, maybe, if I started with the left side, say, so f sub k plus 1. Now, here's the thing. K is greater than or equal to 0. So k plus 1, is greater than or equal to 1. So this subscript is greater than or equal to 1. But that's not greater than or equal to 2, though. Right? All the time, if k equals 0, then k plus 1 is, greater than, well, k plus 1 would be equal to 1, which is not greater than or equal to 2. So this particular usage of the, this particular usage of the sequence rule wouldn't apply. But, we already showed that when k equals 0, it's true. So we would then start, our next thing would be when, then, we've shown that it's true for k equals 0. Now if k equals 1, k plus 1 equals 2, and that's greater than or equal to 2. So really, we're showing for integers k greater than or equal to 1 that this statement is true. See, it gets messy. And if I say, okay, well, if I'm at k equals 1, and then I apply this, well, that rule that f of k would equal to, f sub k minus 1, the previous rule, right? If k is equal to 1, right, then k plus 1 is 2, so we can use our rule here. Then f sub k plus 1 would be equal to f sub k, the term before it, plus f sub k minus 1. And I know see, our induction hypothesis involves f sub k. All right. I know that that's going to be less than or equal to 2 to the k. But what the heck do I do with this? All right, what do I do with f sub k minus 1? The 2 terms back. I was like, oh man, I don't know. So you see, there's an issue with standard induction for a proof like this. Problem. We have a problem. So we got to fix that. We got to get around that somehow. So standard induction wouldn't be good for proving this particular statement. And it really has something to do with the fact that you're going back 2 terms instead of just 1 term. It really does have to do with that fact. The fact that you're going back 2 terms in the sequence will really, indicate to you that you need 2 base cases instead of 1 base case. All right, and that's what we're going to get into now. Establishment of more base cases and a stronger assumption We need a stronger assumption. I not only need to assume something about k, but also about fk minus 1. So we need more in our assumption as well, in our inductive hypothesis. So you see, however, since f sub k plus 1 is defined in terms of fk and fk minus 1, the proof requires a bound on both fk and fk minus 1 in order to upper bound fk plus 1. But we only have the one for fk, right? That's the problem. Right, the inductive hypothesis for standard induction only provides the bound on f sub k, not f sub k minus 1. So for the upper bound on terms of the Fibonacci sequence, a stronger version of induction is required. The principle of strong induction assumes that the fact to be proven holds for all values less than or equal to k, and proves that the fact then holds for k plus 1. So not only are we going to assume that it's true for n equals k, but we're going to assume it's true for n equals k, k minus 1, k minus 2, all the way back down to our last base case, all the way down to our highest base value. So by contrast, the standard form of induction only assumes that the fact holds for k in proving that it holds for k plus 1. So you're assuming a lot more here. You have a much stronger assumption, thus the name strong induction. So define S sub n to be the predicate that f sub n is less than or equal to the n, where f sub n is defined by Fibonacci's initial values and recurrence relation. The proof that S sub n is true for all non-negative integers n has two components. So again, you have your base cases. S sub 0 and S sub 1 are true. You show it's true for n equals 0 and for n equals 1. And you might need more base cases in other scenarios. We'll get to that in a second. Well, several minutes. And then the inductive step. For every k greater than or equal to our highest base value, right, for every k greater than or equal to 1 here, not 0, if the statement is true for 0, 1, 2, all the way up to k, then it will be true for k plus 1. That's a much stronger assumption than just S of k, showing that if it's true for k, then it's true for k plus 1. You're going to assume that it's true for all values up to k, and then show it must be true for k plus 1. All right, so in strong induction, again, the inductive hypothesis is that the statement is true for all values up to k. In regular or weak induction, I guess the standard induction you can call weak induction if you're calling this strong induction. The inductive hypothesis is just S of k is true. Sometimes the inductive hypothesis is expressed using a universal quantifier. The following two ways to express the inductive hypothesis are equivalent. Right? So saying that S sub 0 all the way up to S of k is true is equivalent to saying that for every j in the range 0 through k, S of j is true. So equivalent. So again, look, they're comparing them. Weak induction to strong induction. Remember, this is previous two sections, weak induction. You're saying, for all k greater than or equal to some value, S of k implies S of k minus k plus 1. So, like, if S of 1 is true, then S of 2 is true, and then if S of 2 is true, then S of 3 is true. If you get all the integers, sure. But over here in strong induction, you're saying for all k greater than or equal to 1, you assume it's true for all values, up to k, and then show it's true for k plus 1. So here I assume it's true for 0 and 1, show it's true for 2, and then if it's true for 0, 1, and 2, it must be true for 3, And if it's true for 0, 1, 2, and 3, it must be true for 4. And if it's true for 0, 1, 2, 3, and 4, it must be true for 5. So you got a lot more going on. So I'll do these, and we'll get to eventually a proof. Actually, I'm going to prove that theorem I stated a second ago, with the Fibonacci numbers. We'll prove that with strong induction in a minute. Just want to go through rehashing the steps here. So here, suppose that the inductive step of a strong induction proof shows that for k greater than or equal to 1, if S is true for 0 and 1 and 2 and all the way up to k is true, then sk plus 1 is true. So what statement is equivalent to the inductive hypothesis, right? This is the inductive hypothesis. What you're assuming that the statement is true all the way for every integer up to k, and then you're going to show that it's true for k plus 1. So, for k greater than or equal to 1, and any j in the range from 0 through k, S of j is true. That's what you're going to assume. Now, if you assume this, can you conclude that S of k minus 2 is true? Yeah. Because if you're saying it's true from 0 through k, k minus 2 is between 0 and k. So the statement would be true for k minus 2. You'd be oh, wait, what? Oh. Yeah, that's right. This is for any k, right? And k minus 2, what if k was 1? K minus 2 would go below 0. So you can't always assume that. My apologies. What if k were 1? Now, if k were greater than or equal to 2, and you assumed it was true from 0 through k, then you could say k minus 2 was true. It's true. But if you assume this for k greater than or equal to 1, and any j in the range from 0 to k that the statement is true, can you assume that S of k minus 1 is true? This is yes, because k minus 1 would be greater than or equal to 0, would be in this range all the time. So yes. Okay, and then, again, this is kind of trial and error. There is no simple rule, and like I said, I'm going to go through the proof of this with strong induction in a minute on paper. But there's no simple rule to determine when strong induction is required instead of weak induction. The best method is to try proving the inductive step using only the preceding value. Try proving the theorem for k plus 1 using only k. If that fails, then try a stronger inductive hypothesis. The inductive proof showing a bound on the Fibonacci numbers given below would fall within standard induction because bounds on fk and fk minus 1 are required. Would fail. I showed you how it would fail because bounds on fk and fk minus 1 are required to prove the bound on fk plus 1. Alright, so back here. Same statement. Alright, same statement. But this time, I'm going to go through and prove this with strong induction. So same statement. Now I'm going to get into the proof, and this is by strong induction on n. Right. So first, the base cases. Now, like I said, sometimes it's trial and error. You're going to have to play around with it. But in general here for sequences defined recursively, because we have to go back here in our definition of the sequence, we have to go back 2 terms. Probably going to need 2 base cases. So I'm going to start off with 2 base cases and see if that's enough. And it should be here. Right? But let's see. All right, so I'm trying to prove that, the nth Fibonacci number is always less than or equal to, 2 to the nth. That's for all n greater than or equal to 0. So I'm starting, my first base case is when n equals 0. Now I've already shown this, right? Is f sub 0 less than or equal to 2 to the 0? Yes, 0 is less than or equal to 1. So this base case is true. But again, I'm going to also do it when n equals 1. Right? Because when I didn't do a second base case last time and get a stronger induction hypothesis, things fell apart. Right? Couldn't prove it. So when n equals 1, look at f sub 1. Is that less than or equal to 2 to the first? Right? Replace n with 1. Well, f sub 1 is 1. Is 1 less than or equal to 2? Yeah, okay. So far I've shown this is true for, the first two integers, 0 and 1, the first two non-negative integers. All right, now, the inductive step. So we're trying to show that for all k, all integers k greater than or equal to this last base case here, right? Because last time it was 0 because I stopped at 0. Here I'm stopping at 1. So for all k greater than or equal to 1, the following. If this statement is true, so say if f sub j is less than or equal to 2 to the j for j in the range from 0 to k. I'm going to be starting with 0 here. So that means, right, this means the following. This means that, f0 is less than or equal to 2 to the 0, and f sub 1 is less than or equal to 2 to the first, and f sub 2 is less than or equal to 2 to the second, and all the way up to f sub k is less than or equal to 2 to the k. We are assuming all this. This is our induction hypothesis. If we assume all that, then we can hopefully we can show that the statement will be true for n equals k plus 1, that f sub k plus 1 will be less than or equal to 2 to the k plus 1. All right. So let's take a look. So again, we are assuming all of this. Right? This is all assumed to be true. And show that if all this is true, the value, the statement is true from 0 up to k, then, where k is greater than or equal to 1, then we can show that it's true for k plus 1. Right. So now, let's try to show this, right? I'm going to look at f sub k plus 1. Now, this time, the reason we're doing, that's why I went up to 1, really. That's why I did the base cases up to 1. Because I wanted to set it up so that this k plus 1, right, since we're looking at values of k here greater than or equal to 1, the value of k plus 1 is greater than or equal to 2, and I can then therefore apply this rule. Right? Because remember, this rule for the terms of the sequence applies when the subscript is greater than or equal to 2. That's why I would go up to a base case of 1. Right? That's why we needed that extra base case. And since this subscript now is greater than or equal to 2, I can apply that rule that f sub k plus 1 would be equal to the term before it, f sub k, plus the term before that, f sub k minus 1. Right. And also, too, right, k minus 1 is greater than or equal to 0. Right. So, I wanted to make sure that I didn't go down to subscripts below 0, right, because we're trying to prove this true for 0 and greater. Right. And if I, did like I did earlier, if I had k greater than just equal to just 0, k minus 1 could be down to -1, and I don't want subscripts of -1. We're trying to prove this is true for values 0 or greater only. Okay, now, here's where the induction hypothesis is applied. Right, by the induction hypothesis. Now, this is strong induction. This and this are in this segment, in our assumption. We assume the statement is true. Right? We're assuming that this statement is true for all values of k, all values of j, really, all subscripts from 0 to k. So k is between 0 and k, from 0 to k. K minus 1 would be from 0 to k, right? That's why we needed to go to that first base case, because I want k minus 1 to be from 0 to k. So these are both less than, remember, f sub k would be less than or equal to 2 to the k. Plus, and then f sub k minus 1 would be less than 2 to the k minus 1. Now I eventually want to get this to be, like 2 to the k plus 1. Okay, now I want to eventually get this to be less than, or equal to 2 to the k plus 1. Okay, something I notice. 2 to the k plus 1 is 2 times 2 to the k, right? Okay. Okay, so this, I could do this. This is less than or equal to, 2 to the k still, I got the 2 to the k there. Plus the, I still have the 2 to the k minus 1. Now, since k minus 1 is, greater than or equal to 0, 2 to the k minus 1 will be greater than or equal to 1. So definitely positive. So if I add on, if I take this here, if you add more positive stuff to it, you're just going to make it bigger. So this expression is less than 2 to the k plus 2 to the k plus 1 plus another 2 to the k minus 1. And then these together, this is equal to 2 to the k plus, and then 2 times 2 to the k minus 1, which is another 2 to the k. This is 2 to the k plus 2 to the k, which is 2 times 2 to the k, which is 2 to the k plus 1. Okay. So I've shown by applying the induction hypothesis to both these terms here. Right? This would be less than 2 to the k. This would be less than or equal to 2 to the k minus 1 by our induction hypothesis. We have now shown that if the statement's true from 0 up to k, it's going to be true for k plus 1. Right? F sub k plus 1 is less than or equal to 2 to the k plus 1. And since we've shown the base cases, we've shown it's true for 0, it's true for 1, and by our induction step, if it's true for 0 and 1, it must be true for 2. And if it's true for 0, 1, and 2, it must be true for 3. If it's true for 0, 1, 2, and 3, it must be true for 4, and so on and so forth. So the statement must be true for all integers greater than or equal to 0. So putting all this together, therefore, the nth Fibonacci number is less than or equal to 2 to the nth power for all n greater than or equal to 0. And there's the end of our proof. But it's a lot stronger. Right? Our assumption, our inductive hypothesis is a lot stronger than the inductive hypothesis from regular or standard induction or weak induction. But again, you may also need some more base cases to make sure that you're not going to certain subscripts. Make sure you might need more base cases, and that'll be by trial and error sometimes. You got to figure out, this value is not going to be satisfying what I'm trying to look at. I want all my subscripts to be greater than or equal to 0. So k minus 1 needs to, k needs to be greater than or equal to 1, not 0. So I need to go from base cases up to, I need to have base cases up to 1. Not just the first base case. So it takes some practice, it takes some doing. And we'll look at another example of something like this in a minute. And again, they read through it here. They got their proof here. It's pretty much the same thing I did. Yeah, they added on that extra 2 to the k minus 1. Yeah, pretty much the same thing I did to show that it's true for the k plus first, when n equals k plus 1. Alright, so here they get into, like I said, you saw in the last example, I had 2 base cases. Sometimes you're going to need multiple base cases when doing a proof by strong induction. Right, so the predicate S of n may be true only for n greater than or equal to a particular value, denoted below by a constant a. Also, the base case may require proving the assertion directly for more than one value, right? Having more than one base case. The base case for a proof by strong induction establishes that S of n, the statement, is true for n equals a through n equals b, where a and b are some integers, right? Some constants. The inductive step then in a proof by strong induction assumes that S of j is true for all values of j in the range of a through some integer k, which is greater than or equal to the last value of the last base case b. So for all k greater than or equal to b, S of j is true from the first base case all the way up to k, and then proves that the theorem holds for k plus 1. So again, kind of like what just happened up here in this proof. And they're rehashing that here. So here's the principle of strong mathematical induction. So let Sn be a statement, parameterized by n, a positive integer, and a statement about the integers. Let a be less than or equal to b be integers. Then Sn is true for all n greater than or equal to a if the following 2 conditions hold. So here's your base cases, right? If S is true for n equals a plus 1, all the way up to b, and for values of k greater than or equal to b, if the statement's true from a to k, then it's true for k plus 1. If you can show that, then you'll have shown that it's true for all integers greater than or equal to a. And again, they're running through. I guess they really want you to get this down. Of course they would. So base case, you show multiple base cases up to b. Then for k greater than or equal to b, you assume that the statement is true from the lowest base case up to k, and then use that to show that the statement is true for the next integer up. And again, showing all that here. And then again, there's kind of hashing going through here, like what would you need to show? What kind, can you get the steps down? Do you know the steps? All right, so here, consider an inductive proof in which the inductive step is for all k greater than or equal to 6. If p of 3, p of 4, all the way up to k are true, then p of k plus 1 is true. If this was the inductive step, what must be the base case? Well, you see it's for all k greater than or equal to 6, and they're starting here at 3, so that means you would have had to shown that the statement's true for 3, 4, 5, and 6 to be your base case. And then if you show that this is true, then basically you'll have shown that, oh, it's true for 3, 4, 5, and 6, therefore it's true for 7, and then it's true for 3, 4, 5, 6, and 7, therefore it's true for 8, and so on. All for the rest of the integers greater than or equal to 3. Alright, here select the choice that is equivalent to the following statement. For k greater than or equal to 7, if p of j is true for all j in the range from 2 to k, then p of k plus 1 is true. Well, again, this is for k greater than or equal to 7. They're saying here p2 to p, we're assuming 2 to k is true. Then k plus 1 is true, so that'd be this statement here. And again, just kind of, do you know how to set up the steps is what they're doing here. Alright, so another strong induction example. Buying cans of juice in 3-packs or 4-packs. Alright, so suppose that cans of juice come in packs of 3 or 4. We would like to be able to buy n cans of juice by purchasing a combination of 3-packs or 4-packs. For which values of n is this possible? So let P of n be the assertion that it is possible to buy n cans of juice by purchasing only 3-packs or 4-packs. And we see just some examples here. P of 7 is true because you can buy a 3-pack and a 4-pack, right? You get seven cans. P of 5 is false, right? You can't buy, if you have just 3-packs and 4-packs, you can't get 5 cans. There's no way. So we will use strong induction to prove that for any n greater than or equal to 6, P of n is true. Alright, you know what? In fact, I'm going to go through this and we'll prove this on paper on our own and come back to this. Alright. So 3-packs and 4-packs of juice. Alright, we can only buy 3-packs and 4-packs. And again, the statement P, the predicate P of n is, you can buy n cans of juice. So we see that, P, obviously P of 0, why would we 0? P of 1 is false, right? You can't buy just 1. P of 2 is false. Can't buy just 2. P of 3 is true, right? P of 4 is true because you can buy just a 3-pack or just a 4-pack. We saw earlier they said P of 5 is false, right? Can't buy just 5 cans. Now P of 6, true. 2 3-packs. P of 7, true. A 3-pack and a 4-pack. P of 8, true. 2 4-packs. Now, because there's a 3-pack, see how I've got 3 trues in a row here? Since it's possible to buy 6, I can just add a 3-pack and then get 9. So P of 9 is true. And then do the same thing. Since it's possible to buy 7, just add a 3-pack and you can get 10. All right. Just add a 3-pack and P of 10 is true. And then I just keep doing this. Since it's possible to buy 8, add a 3-pack, then it's possible to buy 11. Since it's possible to buy 9, add a 3-pack, then it's possible to buy 12. And I could do that forever. But notice it's only from 6 onward. So that's why they're saying, can you show that P of n is true for all n greater than or equal to 6. So again, I kind of outline what's going to be happening here. So we'll do a proof by strong induction on the value of n. Now, let's think about how many base cases we're going to need. Now, obviously I want to start with 6. So I need at least to show, it's easy to show, I already talked about it, 2 3-packs. Now that wouldn't be enough, right? Because if I said just show that it's true for 6, let's work it out. All right. So if I did one base case, let's see what happens when I do only the one base case. So when n equals 6, P of 6 is true. I can buy 6 cans with 2 3-packs. True, right? It's true. Okay. So I've shown it's true for at least n equals 6. Now let's say we didn't know we needed more base cases. We do need more base cases, but let's say that we didn't know that. And then let's jump to the inductive step. Now I'm doing strong induction here. So we're going to try to show that for all, k, now I stopped at 6 earlier. So I'm going to say for all k greater than or equal to 6, if, P of 6 and P of 7, I guess, up to P of k is true. Another way to say that is if P of j is true for all j from 6 to k, right? That's probably a better way to say that. If P of j, if the statement's true for all j, for all integers from 6 to k, then let's show that P of k plus 1 is true. All right. So here's our inductive hypothesis, and we're going to see in a second. We're going to see in a second that I need more base cases. Let's look at purchasing k plus 1 cans. I'm trying to see if I can purchase k plus 1 cans with only 3-packs and 4-packs. Now we know that k is greater than or equal to 6 here, so that means k plus 1 is greater than or equal to 7. I'm just adding 1 to both sides. Now in order to be able to buy k plus 1 cans, in order to be able to buy k plus 1 cans, you either need you need to buy be able to buy up to 3 less or up to 4 less, right? Because you can only add on 3 or 4. So you need to be able to buy either k minus 2 cans or k minus 3 cans. Right. But let's take a look at k minus 2. If k is greater than or equal to 6, k minus 2 would be greater than or equal to 4. But what if this was 5? Something greater than 4 is 5. You can't buy 5 cans. Right? We saw that you can't buy 5 cans. So what I need to happen here, I need k minus 2 to be greater than or equal to my lowest base case. I need k minus 2 to be greater than or equal to 6. And if that's the case, if k minus 2 is greater than or equal to 6, that means I need k to be greater than or equal to 8. That means we need base cases up to 8. So I have too few base cases. We need base cases up to 8. I hope that made sense, right? Again, based on, I'll go through that one more time. If I'm trying to buy k plus 1 cans with 3 packs or 4 packs, let's say I need to be able to buy k minus 2 cans. Right? And I assumed it was true up to k, so k minus 2 cans, I should be able to buy k minus 2 cans or k minus 3 cans and then just add a 3-pack or a 4-pack. But if k is only greater than or equal to 6, if my only base case was 6, k minus 2 would be greater than or equal to 4, but there's a number greater than or equal to 4 we know you can't buy that number of cans for, right? 5 is, what if k was 7? 7 minus 2 is 5. 5, you can't buy 5 cans. So I need k minus 2. I want this k minus 2 to be greater than or equal to my lowest base case, the value of 6. And the only way that's going to happen is if k is greater than or equal to 8. So I need base cases up to 8. So I'm going to go back here and add on the base cases. Now, this is true. We saw, you get a 3-pack and a 4-pack. And P of 8 is true. You saw 2 4-packs, right? So now I have these 3 base cases, and now my inductive step is for all k greater than or equal to 8, we're going to assume that P of j is true for all j from 6 to k. So we're starting at least from 6, 7, and 8. We have 6, 7, and 8 down, and then we would try to prove that it's true for 9, then true for 10. Now, when I'm trying to purchase k plus 1 cans, and k is greater than or equal to 8, k minus 2 is greater than or equal to 6, and this is a value that we know is in this range. So you can purchase, so by our induction hypothesis, this is really jumbled, but by our induction hypothesis then, we can purchase k minus 2 cans, right? Again, since k minus 2 is going to be in this range from 6 to k, it's greater than or equal to 6. And then just add a 3-pack. Implying that P of k plus 1 is true, right? Oops. We can purchase, by our induction hypothesis, since, k minus 2 is going to now be in this range from 6 to k, it's greater than or equal to 6, we can purchase k minus 2 cans and then just add a 3-pack to purchase the k plus 1 cans. So we have shown that if all these are true, if you can purchase anywhere from 6 to k cans, you can purchase k plus 1 cans. So then going back to our, we showed that we could purchase 6, 7, or 8. Then this implies that we could purchase 9. And if we can purchase 6, 7, 8, or 9, this implies that we can purchase 10. And then 6, 7, 8, 9, or 10 implies that we can purchase 11 and 12 and so on. Forever. All greater than or equal to 6. Therefore, this was very jumbled. I do apologize. But therefore, P of n is true. You can purchase any number of cans for that number being greater than or equal to 6. Right, and that's exactly what, now, again, this was jumbled because I started off with the wrong number of base cases. And I wanted to show you, like, you'd probably eventually be able to figure out, ooh, I need more. Because when I started off with just the one base case and had k being greater than or equal to 6, then k minus 2 wouldn't be in a very good range, right? Because I'm going from 6 to k minus 2 would be greater than or equal to 4. So there's some values that weren't in that range. It's like, ooh, I need more base cases. I need enough base cases so that when I took away a 3-pack, if I wanted to get k plus 1 cans, I needed a 3-pack. When I took away a 3-pack, that'd be k minus 2. I need k minus 2 to be in the range from 6 to k. I need to be greater than or equal to 6. That's why I needed to go to 8. So that k minus 2 could be greater than or equal to 6. And they explain all that here. Say they want k minus 2 to be greater than or equal to 6 and all that. Now I could have done the same thing with the 4-pack. Instead of, if I'm trying to buy k plus 1 cans, I could have said, if I can buy k minus 3 cans, if k minus 3 is in the range from 6 to k, then I could just add a 4-pack and get k plus 1 cans. So if I was doing the argument with k minus 3 instead of k minus 2, then I would have had to have k minus 3 be greater than or equal to 6, be in that range from 6 to k. So then k would have to be greater than or equal to 9. And if I was using that k minus 3, I would have to have added another base case, 6, 7, 8, and 9, and then talk about adding 4-packs instead of 3-packs. Right, so this is pretty jumbled, but again, hopefully after a little bit, after practice, you'll recognize, and maybe even reading some of the proofs too, reading these proofs in the exercises, looking at the solutions, maybe just one or two of them ahead of time, seeing how they're doing things. You get a feel for how many base cases will be needed. So you see they did that here, 3 base cases. You can buy 6, you can buy 7, you can buy 8. Now for k greater than or equal to 8, assume that you can buy j cans where j is anything from 6 through k. And then you got to show that k plus 1 is true, right? You can buy k plus 1 cans. Now, again, you can buy k minus 2 cans because k minus 2 would be greater than or equal to 6. It falls from 6 to k. That's the induction hypothesis. And then you just add a 3-pack. Right? Since you can buy k minus 2 cans, you add a 3-pack, you can buy k plus 1 cans, so p of k plus 1 is true. They do a little animation here as well. Right? I ask you to watch this animation. So like I said, how many base cases are necessary? How did we know to use 3 base cases in the example of the cans with 3-packs and 4-packs? To some extent, determining how many base cases are required in a strong induction proof requires some trial and error, like I showed you. But there are some basic principles that can be applied. Again, they went back to k minus 2. Again, you could have gone back to k minus 3 and had to go base cases 6 through 9, as I mentioned, if you were talking about adding a 4-pack. So yeah, sometimes it'll require trial and error to know how many base cases are necessary so that my strong induction hypothesis will actually help, when I'm trying to do that inductive step. All right, so let's look at this one. So it's a very similar problem. Consider again the problem of purchasing cans of juice. Suppose now that the juice is sold in 2-packs or 5-packs. So let Q of n be the statement that it is possible to buy n cans of juice by combining 2-packs and 5-packs. This problem discussing uses strong induction to show that, for any value of n greater than or equal to 4, Q of n is true. So you can buy any number of cans 4 or greater. Now let's think about the end. All right, let's think about the end. The inductive step. I would have to assume that for values of j from 4 to k, the statement is true, and then show that I could buy k plus 1 cans. All right, show that the statement is true for k plus 1. All right, let's think about this. If I want it to be true for k plus 1, that means I want to be able to buy k plus 1 cans. But I only have 2-packs and 5-packs. Well, let's just use the 2-pack. So if I want to buy k plus 1 cans, I would have to be able to buy k minus 1 cans and then add a 2-pack. So I want k minus 1 to be in the range from 4 to k, so that my induction hypothesis holds, is true. So I want k minus 1 to be greater than or equal to 4, meaning I want k to be greater than or equal to 5. So I need to do base cases up to 5. So for n equals 4 and n equals 5, right? So obviously you can buy 4 cans, you just do 2 2-packs. You can buy 5 cans, do a 5-pack. So those are true. And then if it's true for every value from 4 to k, then it will be true for k plus 1, because like I said, you can go from, you can buy k minus 1 cans, because k minus 1 will be from 4 to k, and then you just add a 2-pack, and then you can buy the k plus 1 cans. So it's a pretty similar argument, but only 2 base cases there. Now if you use the 5-pack, you'd have to have 5 base cases, 4, 5, 6, and 7, and 8. So the inductive step will prove that for k is greater than or equal to 5, right, q of k plus 1 is true. What is the inductive hypothesis? So again, that q of j is true for any value from 4 to k. And then you prove it's true for k plus 1. The inductive step will prove that for k greater than 5, q of k plus 1 is true. What part of the inductive hypothesis is used in the proof? Again, that 2 can't, just take a 2-pack away, that q of k minus 1 is true. And then you just add a 2-pack. And then in the base case, for which values of n should q of n be proven? I mentioned 4 and 5. All right. Now, I will leave you to read this proof of the prime factorization of integers. This video is almost an hour now. But again, they're using strong induction on, on the value of n and whether or not it can be expressed as a product of prime factors. All right, so please read through this. They're doing the same kind of proof. It's not like the cans thing exactly, but they're using strong induction to prove that any integer greater than or equal to 2 can be written as a product of prime numbers. All right. Then you have the other major concept in this section, the well ordering principle. It's a simple concept. It's about positive integers or non-negative integers. All right. The well ordering principle says that any non-empty subset of the non-negative integers has a smallest integer. So if you look at the non-negative integers, right, that's 0 and greater, take any non-empty subset of that set. It's going to have a smallest integer in it. Right? There will be some smallest element. And anything you can prove with mathematical induction or strong induction, you can prove using the well ordering principle, and you can really do it by using proof by contradiction and looking at the set of integers for which the statement is false and applying the well ordering principle and coming to certain contradictions. So you can read through this stuff here in the division algorithm. I'm just going to get to this last activity here. Oh, it looks like I already did it. All right, anyway. So the well ordering principle, again, just all the well ordering principle states is that any subset, any non-empty subset of non-negative integers is going to have a smallest integer. So like I said, you can use this principle to prove any statement you could have proved by induction. You can prove with the well ordering principle, and you can do it by contradiction. And I'll show you an example here. So the well ordering principle can be used to prove any fact which can be proven by standard or strong induction. So consider again the problem of purchasing cans of juice. Suppose that juice is sold in the 2-packs or 5-packs again. So let Q of n be the statement that it is possible to buy n cans of juice by combining 2 packs and 5 packs. We can use the principle of well ordering to show that for n greater than or equal to 4, Q of n is true. So again, what we're going to do is prove this by contradiction. All right, we're going to prove this with the well ordering principle by contradiction. So this statement is, for all n greater than or equal to 4, Q of n is true. Let's suppose the opposite of that is true. Let's suppose that for not all n greater than 4, the statement is true. That means that for some values, maybe just one, but for at least one value greater than or equal to 4, Q of n is not true. Now that means that we're assuming, all right, so I'll write this down. All right, I'll write this down. Okay, so here's that statement. And you got 2 packs of juice, 5 packs of juice. Q of n is a statement, you can purchase n cans. We're asked to show that for all n greater than or equal to 4, Q of n is true. Now, we talked about it with strong induction earlier, showed that this was true. This will be a proof by contradiction using the well ordering principle. All right, so by contradiction, so we're going to assume the opposite of this is true. Now the opposite of this statement is that assume there is at least one value right? The opposite of for all is there is, right? Assume that there is at least one value greater than or equal to 4 such that Q of n is false. So what this means, by the well ordering principle, because these are non-negative integers we're talking, by the well ordering principle, the set of integers, right, the set of integers, non-negative integers, because we're talking greater than or equal to 4, the set of non-negative integers n for which Q of n is false has a smallest value. Let's say m. Right? So again, that means that m is some value greater than or equal to 4, and Q of m is false. Right? You can't buy m cans using 2 packs and 5 packs. And again, m is the smallest value for which this happens. So that means if there's any value less than m that's greater than or equal to 4, the statement will be true. Right? So this means from 4 up to m minus 1. Right? So another thing this implies, this would also imply that Q of 4, all the way up to Q of m minus 1 must be true, right? Because again, all these values are smaller than m. Now, this will lead us to a contradiction, and let's see how. Right? We can see that in the activity. So again, to which set should the well ordering principle be applied? To the set of all n greater than or equal to 4 such that Q of n is false. Right? I said that earlier. Right? This set is non-empty if we assume, again, by contradiction, that there is a value greater than or equal to 4 such that this is false. That set will be non-empty, therefore, by the well ordering principle will have a smallest value. So again, let M be the smallest value from that set. Select the statement that correctly describes M. Well, Q of M is false, but for any j in the range from 4 through m minus 1, Q of j is true. I just said that too, right? Any value from 4 to m minus 1, the statement will be true, because m should be the smallest integer greater than or equal to 4, such that Q of m is false. And then, where's the contradiction? Right. Now, we have to find a contradiction for every value greater than or equal to 4. Right. Now, what is the contradiction that results if m equals 4 or m equals 5? All right, well, m equals 4, if m equals 4 makes it false, that can't happen, because we already know you can buy 4 cans. Right? You can just buy 2 2-packs. So in that case, Q of 4 would be false and true at the same time, a contradiction. Same thing for when m is 5. If I'm saying that the smallest value in this set is 5, well, that would mean Q of 5 is false, but you can just buy a 5-pack. So Q of 5 is true. So Q of 5 is false, Q of 5 is true. You get a contradiction in either case, because it is possible to buy 4 cans and 5 cans. Right? So Q of 4 and Q of 5 are true, but we'd be saying Q of 4 and Q of 5 are false if we said that m was 4 or 5. So there's a contradiction there. Now what about values higher than 5? What about values 6 or greater? Where's the contradiction? So if I said, some value 6 or greater was the smallest value for which Q of m was false, well, remember, every value below that, from 4 to m, from 4 to m minus 1, would make it true. Well, 4 to, m minus 2 is 4 or greater, so m minus 2 would make it true. And then you can just add a 2-pack, so that would mean Q of m and Q of is true and false. Right? Because if m is greater than or equal to 6, then m minus 2 would be greater than or equal to 4, which is in the range from 4 to m minus 1. Right? So m minus 2 would make it true. And then if that's true, if you can buy m minus 2 cans, you could just buy another 2-pack and get m cans. So Q of m would be true, and it would also be false, because we said it was false. There's a contradiction there. So it is possible to buy m minus 2 cans. Right? M cans can then be purchased by buying m minus 2 cans and a 2-pack. So you'd say it was possible and impossible at the same time to buy m cans. There's a contradiction. So for 4 and up, there's a contradiction, meaning that our original statement must be false, meaning the statement in question, the theorem that they stated, was true. You can buy any number of cans from 4 or greater using 2-packs and 5-packs. All right, so a lot going on here. And I would say, learn your strong induction principle. Again, you're going to have to play around to figure out how many base cases are necessary. And then you have your strong induction, the inductive step, where you're assuming that, every value up to k makes the statement true. From your lowest base case value up to k makes it true, and then you're showing that the statement is true for k plus 1. And with all the base cases and the inductive step, you'll have shown that the statement is true for all values, greater than a certain value. Which you could also prove with this well-ordering principle. Right? You assume, by contradiction that the opposite is true, and then apply the well-ordering principle to the set of integers that make a statement false, as was done here in this activity. Right. So then you got some additional exercises. Again, I haven't assigned all of them, just some of them. I'd still recommend looking at them all, though. Maybe even reading some of the solutions, of the ones you're not assigned. But for the problems you are assigned, please wait to look at the solution. Try to work it out ahead of time. The ones you aren't assigned, I'd take a look at the solutions and see how they're doing things, because again, this can be a bit tricky. especially determining how many base cases you're going to need. But still, try to work on things before you look at the solutions. You know, you're not going to learn anything if you just look at the solutions and copy them down. And of course, if you have any questions, let me know throughout the not throughout the week, but just let me know anytime. You know, whenever you get to this. Hopefully, I was able to explain things in a reasonable manner. This can be a bit tricky to explain for me. Like I know what I'm doing. I just the explanation part is kind of lacking. I feel on my end. You saw how jumbled my first proof was here. So again, if you have any questions, let me know. Hopefully, I can clarify things a little better for you. And thank you very much for watching.